Okay, so you may have heard of n factorial before. So n factorial would count the number of arrangements of n objects. 1 factorial would count the number of arrangements of one object, and there's only one way to do that. And 2 factorial would count the number of arrangements of 2 objects. So if it was 2 objects A and B, we could have AB or BA. So that would give us that 2 factorial is 2. And in general, n factorial would be the product from 1, 2, 3, all the way up to n. One question you might ask is, what would be a natural number to assign to something like a half factorial? What if we wanted to find the factorial of numbers that aren't whole numbers? And so here's one way you can try and extend the factorials. There's many different ways to do it. You might have seen perhaps the integral definition, but some of those are not obvious. And here's maybe something maybe you might have thought of yourself. So here's something I want you to think about. So here's a way we could possibly kind of loosen n factorial. So this is something called a Pochhammer symbol. So what it does is it sends x to this polynomial. So you can notice that if you set x equals 0, then this just gives you n factorial. And one thing you might want to have a look at is what happens if you just take this, and then you divide by s of n like this. So what you're doing is you're taking this and then you're skewing it across by s. So we have this being 1, 2, 3 up to n. And this instead would be starting from s plus 1, s plus 2 up to s plus n. Now what we can do is try and align them up and then cancel the terms that are aligned up. So let's have a look at a small example. So if we have 5 of 0, 5 over 3, 5 like this, we can have 1 times 2 times 3 times 4 times 5, and over here we're going to try to line them up. So this would start at 3 plus 1, and that would be 4 times 5 times 6 times 7 times 8, and we can cancel these terms out. Okay, and what we have left remaining is 0 of 3 divided by, this would be starting from 6, so it's actually 5 and Pochhammer symbol 3. If you want, I recommend you to go away and see and check for yourself, maybe prove it or something else. I'm not going to try and prove it here, because I don't think that's kind of the point. I'm trying to explain how you might think of this yourself and not give like a rigorous formal proof. It's not difficult to prove this, right? You're just cancelling terms. Or you can do this by induction even. And here's the general pattern we get. 0 of some number n, s of n, this would be equal to 0 s over n of s. So it's kind of symmetric. Here's what we'll do. We kind of want to extend the definition, kind of motivated by this idea. We're going to, so this top part would just be s factorial. And this bottom part, well, we'll just leave it as it is for now. So what we want to think about is what would happen if n is really large. So if we write this bottom part down, we have n plus 1, n plus 2, up to n plus s. And you want to think about what would happen if we divided this by n times n all the way up to n like this. So s lots of n. And I want to think about each of these divisions. So here's how I want you to think about it, right? S is a small number, and n we want to grow. We want to grow to infinity. So what we're doing is taking the limit as n approaches infinity. If we do this, and so we're taking the limit up as n to the s over this Pochhammer symbol. And when we do this, right, think about it this way. Think about it like your age and the age of like a sibling or something. You and a sibling, maybe when you're really young, maybe if he's 4 or 5 years younger than you. When you're 10, for example, he's half your age. But when you grow up and you're like 100, he's at 95% of your age, right? So the ratio between your ages gets closer and closer to 1. And that happens for each of these. And actually, because there's only a finite number of them, this is a formal argument, there's only a finite number of them, we'd actually take the limit of the product as a product of the limits. So you can just say, oh, this goes to 1, this goes to 1, this goes to 1. So we can just multiply 1s together. And this limit actually goes to 1. So this is the limit as well here. Okay, and how is this useful? So what we're going to do is we're going to multiply this side of the equation by n to the s, I'm going to multiply this side of the equation by n to the s. So what do we get? We get s factorial n to the s over ns, which is this side. We're going to do the exact same thing to the other side. 0 n as n like this, n to the s. And we're going to send both sides to infinity. So lim n goes to infinity, lim n goes to infinity. Alright, this we said goes to 1. So, and this s factorial, it doesn't change when we change n. So we get s factorial is equal to the limit as n goes to infinity, n to the s, because it's switched, and then 0 n over s. Okay, so it might not be clear right now exactly how we've improved the factorial, but we can just plot this on Desmos, right? And then we can kind of see what's going on. So I've just made the Pochhammer symbol on Desmos. So this is the Pochhammer symbol of s sub n. I can't do the same notation, but this is what it is. This is the ratio thing we had, which we're taking to the limit, and we can make n bigger and bigger. So this is what happens if n is 1. This should give us s factorial. So right now it's saying 1 factorial is 0.5. But that's because the n is really small. If we make n bigger, you can see it's actually getting closer and closer to 1. And if we try 2, and it's saying it's 2 factorial is 1.5, but if we make it even bigger, like 100, then look, it's very close to 2, which is what it should be. And 3 factorial, it should say 6, but it's just going to give us 5.6. And if we made n bigger, then it will get closer to the right answer. And here's the cool thing, right? We can now, using this idea we've come up with, the Pochhammer symbol, we can actually work out 1/2 factorial, right? Just by extending the definition using the Pochhammer symbol. And we get this number here. And if you notice, this number is very close to this number, square root pi over 2. And actually, it turns out that these two are equal. And we'll actually maybe talk about why in one of the later videos. So this is what I want to show you. Kind of, this is what the factorial would look like when you extend it, right? It's a pretty cool function. Very nice, smooth curve. And so that's kind of what I wanted to say. And perhaps in the next video, we'll have a look at some other representations of n factorial. Okay, thanks for watching.